Hi, everyone. Thank you for joining us on our modeling talks today. We are very excited to have Professor Burkhard Militzer from UC Berkeley joining us today. A little bit about Professor Militzer. He is a professor of planetary science at the University of California, Berkeley. He is the director of the Center for Integrative Planetary Science. Since 2007, he has been on the faculty of the Department of Earth and Planetary Science and the Department of Astronomy. He has a background in condensed matter physics and received his PhD from the University of Urbana-Champaign in 2000. Today, he works on understanding the interiors of giant planets with NASA missions Juno and Cassini. He also studies matter and extreme conditions with computer simulations. Thank you again, Professor Militzer, for joining us today.
Well, thank you, Kate, for the introduction. I'm glad to be here. I would like to give you a little bit of a review what we do in our group that helps us understand the two largest planets in our solar system. And from the planetary science point of view, it's spectacular. We just have one mission in orbit around Jupiter. That's the Juno mission. And just one ended. That was the Cassini mission. That was a flagship mission that was in orbit around planet Saturn for 13 years and made remarkable measurements. So I want to just give you a review how our understanding of those two planets changed because we have these new spacecraft measurements. So I want to tell you a little bit how they what was measured and how it shaped our understanding and how my work contributed to this large endeavor. So in principle, we teach our students that our solar system formed out of a big cloud of gas. We approximately know its composition by looking in the sun today, and that pretty well reflects what was there initially. And in the process of making our solar system, that cloud of gas actually collapsed and made it into a disk. And in this disk, also the heavy elements concentrated, and they started forming planets, as shown in this little cartoon here, and then they orbit around our forming sun. You see this process in motion in other systems. There's a famous ALPHA mission from the ALPHA array where they see one of those disks almost flat on, and they see these gaps. The gaps are indicative of possibly forming planets that carve out a little area where there's less gas and dust, and therefore you can see this. Although we're not quite sure where these planets are, this is pretty well accepted that there's planet formation going on in this now very famous image. In principle, planet formation, we think, starts from these little planetesimals. They grow from millimeter size to meters, and they collide. And eventually, more and more of these objects collide. They get all these oligarchs. They get bigger and bigger. They maybe get an Earth mass. And eventually, they all form bigger and bigger objects. And once you have about 8 Earth masses, you're heavy enough to attract gas. So this is sort of the core accretion process that we think operated in our solar system and formed all planets. So Jupiter got the biggest gas, and Saturn had to deal with what's left over, and Uranus and Neptune got quite little. That's at least the standard view how giant planets form. And in principle, these cores that should be left over, they can in principle erode and redissolve in this gas cloud, but we're not sure whether there's enough energy to bring up heavy material against the gravity. So this is in principle a big planet like Jupiter that has 300 Earth masses. So the core that triggers its formation is relatively small, and as a result, there's still some controversy what the properties of this core is. If you don't want to believe any of this, there is an alternative theory to this, where you say the giant planets collapsed out of the clouds directly. Similar like a star forms, there's no initial core. And then you could potentially form a core later, but based on what we know and what our computer simulations tell us, this is unlikely, but it hasn't been completely ruled out. But nevertheless, this is our standard view how the solar system formed. So we have 4 small planets, and we have these 4 large planets, and they're large because there was something like an ice line. There were a lot more rocky or solid ice materials in the outer part of the solar system that made that core formation quicker, and that's why these 4 giant planets attracted a lot of gas, while in the interior they were starved in comparison. So just in a note, I want to just point out, every time I teach my course, The Planets, where we walk through all the system, I really like that your company has put together Google Earth and an option to switch into Mars modes, and I send my students to actually look for evidence of past water flows, as you can see. Every time it's big fun, and it's also good people can do this on their own computers. So thank you. In my direct models for giant planets, we think that they have a molecular envelope on the outer part. That's a little thicker here in Saturn. Then there's a region where hydrogen and helium become immiscible, and the helium rains out because it's heavier than hydrogen. It's not like your helium balloons that rise, but no, it actually rains out. And then you have an interior part where hydrogen is metallic. So it's no longer molecular, it's electrically conducting. And therefore, in this region, and comparable here, these giant planets make their enormous magnetic field that dwarfs the magnetic field on Earth. And we assume there is a core in both planets, although we don't exactly know what it's made of. We have very little direct evidence it even exists. But we assume standard assumptions. It was made out of the same stuff that made the Earth. So there would be iron and rocky materials and also some ice. So we think that's still there today. So these were the sort of the typical 4-layer models that existed and were constructed by colleagues in our group as well before these spacecraft arrived. So now let's just see what happens to these models once we have new data. So what we typically do in our group, when we put these models together, we pile layers and layers and layers on top of each other, and then when we're out of rock, we start with hydrogen. And every time we have the pressure, and we need to know how dense and how hot a typical layer of hydrogen and helium is under these conditions. That's not an open question. You have the ideal gas law at low density, but how dense a material becomes at 40 megabars, which is approximately the pressure at Jupiter's core mantle boundary, is a difficult question to answer. So we sometimes run computer simulations to answer that. But also we talk to our colleagues who do laboratory measurements. And this is in Livermore. They had a gas gun where they shoot something at a small target. This is a big laser they put together. It's since been replaced by yet a bigger laser that was supposed to ignite hydrogen. It hasn't done that, but nevertheless, it makes exquisite measurements of the properties of hydrogen and helium, and even reach something like 700 megabars. This is more than we actually need. At Sandia National Lab, there is the Z capacitor bank where they just short circuit a giant capacitor bank. And that is also a way to make a magnetic field that launches a flyer plate, and the flyer plate hits something and it compresses hydrogen or helium to some extreme pressures. So we then compare our calculations to these measurements, and then we use them to make models for the interior. So we're consumers of their results. So then let me just give you an example. How do we relate our models to reality, and how do we benchmark them compared to actually what measured by spacecraft? So the spacecraft measurements are just the spacecraft flies by. It switches off all propulsion so that the spacecraft sails through the planet's gravity field without any other forces being perturbing it besides gravity. So the spacecraft itself is the probe. So then when you're further away and not want to measure gravity, you can make corrections to your orbit. This is an example where the Cassini mission then went inside the rings, and then it became closer and closer and closer to orbits till it actually burned up in the planet itself. So nevertheless, for gravity measurements, the spacecraft itself is the probe. And you collect a Doppler signal, the same way you get speeding tickets with your car, just with a slightly higher precision. Its velocity is tracked from Earth with the deep space network. So what then happens is this information about the Doppler signal that you collect from the spacecraft's motion is translated into an acceleration, and that acceleration is represented by a gravitational field. So that term, you may remember, there's the gravitational constant, the mass of the planet, and the distance. That's the main term for a spherical object. But then there are corrections. So Jupiter orbits once every 10 hours. It's a very oblate planet. It's about 10 times the size of Earth. And then the main correction to this gravity field is a term we call J2. And that is the first term in an expansion of Lagrange polynomials. you want to visualize it, then you can say the first term J2 is the overall oblateness. J4 is sort of has this diamond shape, and then there are these other higher order terms. So you basically have a realistic gravity field that you represent in an expansion, and you can represent them graphically every single term. But basically, that's not how the planet obviously looks like. It's just a mathematical expansion. And our colleagues do this to extremely high precision to determine these J coefficients. These gravity harmonics arrive on my desk in the form of an email or some other way. And then I tailor my interior models to match them. That's how it works.
So, methodological question, what's so special about these J's? I mean, can this just be like sine waves or polynomials, or, I mean, does it actually matter, or is this actually a specific thing that works well for Cassini or Jupiter?
The J's have been known for the Earth to, I don't know, J20 or J30. It's just that the planets are, to good approximation, objects in hydrostatic equilibrium. And that makes them north-south symmetric, for example. And then the J's are just a convenient way to expand the gravity field. So that's just a physics. Yeah.
Well, are they like just functions of a particular family of functions that people have decided are a good approximation for planets specifically?
Yes. So these are the Legendre polynomials. P is the Legendre polynomial.
Okay, so I guess that's my question. Why these polynomials as opposed to Fourier expansion or something else? Or does it not matter? It's just convention?
They're the most convenient expansion. The same way your MP3 file Fourier transforms work very well. You could do other things, but they work very well. For example, mu is a cosine of the polar angle. So you won't have a function that is symmetric as you go around. So therefore, that's the cosine of this angle that's being put in. This goes back centuries. That's the standard way of doing these things. But yes, it's because it's the gravity field of a spherical object. I think that's the main motivation, I would say.
Okay, so I guess what I'm leading for is like a lot of our audience, tries to make funny approximations to stuff using neural nets or whatever. So that's the question of, what motivates this design, and if it doesn't matter, can you? I'm thinking even like wavelet transforms. They're very sensitive to local phenomena, which may be irrelevant for gravity. So maybe that's what I'm trying to get at. What drives such approximations, or why can you not use a random neural net?
So it's driven that we try to represent the global gravity field, and it would be very different. Let's just say, and some people go beyond this and do it differently now. They want to measure and represent the gravity signal that comes from the winds, in particular the Great Red Spot. So that's a very local phenomenon. Then they would represent it by other things, and they use Slepian functions. And in the end, they're mathematically equivalent. But for us, it's, let's imagine you only have a few data points. So the spacecraft flies by 30 times. So you use this plausible assumption to basically, you don't have data up right at the North Pole because the spacecraft comes about here. So therefore, with only a few data points, they make a plausible assumption that worked for other planets in the Earth. So if you represent it differently with a very local function, you have no information to say something like the North Pole, for example. But the data where you actually measured is equally represented. So it's just a convenient choice.
No, it makes sense. Like you have a lot of prior information about planets, and because you have a few data points, you strongly leverage these assumptions, which drives you towards Legendre polynomials.
Exactly. So it's a choice. You could do it differently, but we have a limited data set. So the interpretation is driven by past knowledge. That is true.
Got it. Makes sense.
Okay, so then I just illustrate a little bit. We have two teams, one at the Jet Propulsion Laboratory in Los Angeles, another one in Rome in Italy. And they have to remove all things from their analysis that are not directly related to Jupiter. So there are accelerating forces from the satellites, from the moons in the orbit, from other planets, and there are torques from the sun. And also things like tidal deformations. If you have a moon next to Jupiter, Jupiter will slightly change its shape just because there's a moon there. And when the spacecraft flies by, part of that signal is due to the deformation, to the tidal deformation that was induced. But also other weird things. For example, there's a volcanically active moon Io that generates a torus. Torus has ultra low mass. It doesn't affect the gravity field directly, but once the spacecraft sends a signal, it has to go through that torus. And that the speed of light through a medium is slightly different. And these minute effects are being removed. So the precision of these analyses is amazing. And here I'm just giving you an example. The gravity field is modeled, and then it's compared to the measurements. And then my colleagues who directly analyze the Doppler signal compare the model that they put together and subtract one from the other. Now plotting the residuals between the signal that they have received and the flyby that they've modeled. And this is the typical difference. It's like less than 0.1 millimeters per second. So this is like compared to your car, where you argue with the policeman by like a couple of miles per hour. We're basically talking about a fraction of a millimeter per second with a spacecraft that's in orbit without Jupiter. And this is that's sort of the skill and the care that goes into analyzing these data. And this is probably not the best fit that they have. This is probably, they try to flatten that so that they remove the artifacts more than it's done here already. So I'm not involved in that part. I get these J coefficients already processed. So what my work is basically done, I construct these layers of models for the interior, shown here on the left. And then I calculate the J coefficients. Because once I have a distribution of mass, I have a rotating planet. All layers are on hydrostatic equilibrium. So the planet is essentially fluid at that moment. And once I know the density everywhere, I can calculate the gravity field. And the way I do that, I could calculate it directly by just putting the spacecraft in some location and average and integrate over all parcels of mass. But more conveniently, I'm using the same notation. I calculate these J's directly from the mass distribution in my models, and then I compare with the spacecraft observations. So this is how the sausage is made. They look at the Doppler signal, remove all the artifacts, capsulate the signal they got in a gravity field that's expressed by these J coefficients times the polynomials. And I basically construct interior models and then match these gravity coefficients. And then we say something how big Jupiter's core is, or how deep the helium rain layer is, or whether we don't get any match at all. So let me just say a little bit now specifically to the Cassini mission for Saturn, and then move on and tell you a little about what we learned about Jupiter in the second part of that talk. So the Cassini mission, it's spectacular. It was launched in 1997, and it took a while to reach Saturn in 2004. And it made things we could never measure before. It not only looked at the planet itself, it also flew, for example, through the plume on Enceladus. Enceladus has a water-rich interior, and it sort of has a geyser that pushes material into space, and the spacecraft flew through it and made a measurement. So they tell us there's water and CO2, and that was a remarkable measurement. You see this here. This is like the sun in the background. You actually see the material being ejected into space. From the Cassini mission, it also looked at Titan. So Titan is a hazy moon of Saturn, where we didn't actually know very much what's hidden underneath the hazy layer. Now we know much more. We have radar, and they're basically big lakes. They also landed a probe on it, and then the probe landed here and found these boulders. So when geophysicists found something round, then they basically say, well, there must be some process that made it round. And the obvious case, if you have these lakes here, there are also river systems where you basically transported these boulders down, and then they got rounded in the process. The only little surprise here is it's far too cold for liquid water to exist. So the most plausible explanation is that this is lakes of hydrocarbons, so ethane and methane, and they flow down and they carry the rocks, and the rocks, in quotes, are basically water ice. So the best interpretation is this is a rounded boulder made of H2O that's frozen here. So that's something we didn't know before. So we got money before the Cassini mission actually went inside the rings. We got support to prepare models, and we constructed a whole suite of interior models for Saturn, and calculated these J coefficients for our models. And we made different assumptions about the composition, where's the helium rain layer, how big is the core, and all these different assumptions. We had a whole suite of models, and we constructed these ranges. So for example, J6, we were sure would be between 80.5 and 81.7. And then we're expecting the data from the analysis team, and we just dial in the J coefficients and tell them what it actually means, what they measure. That was the plan. We had it all worked out, and we had these hundreds and thousands of models that would all fall in this range. We were ready. So then we were confident that everything would be working because the models we constructed before, they matched the Jupiter data reasonably well. There's still some discrepancy I will come to later, but overall, if you look at the Juno measurements, by the circles compared to the models, at least on a log scale, things looked okay. So then these were our models for Saturn. They all fall this off. This is like the degree, J2, 4, 6, 8, 10. And this is the magnitude of these coefficients. And then our Italian colleague actually sent us the first data set, and they were extremely different. On the log scale, you see that J6 is probably okay, but J8 and 10 are really drastically off. So at that moment, it was clear all of the models we put together, and not just us, other people, were all wrong. There was always something fundamentally missing from everything we've done, all the preparation we've done. So basically you have to make a measurement to learn something completely new. If you do it in a table, you know, J6 was basically around 80 or 81. If we measured 86, and J10 we thought is around 1, it's about 5. So none of the models we had constructed made any sense at that moment. We scratched. The first reaction was there's something wrong with how they process the data, but that was not correct. So the theory was wrong. And the first colleague basically said something, you know, with these J coefficients, you can make sense of them if you put some extra mass around the equator of the planet. It's not the rings. There's too little mass in the ring of Saturn. But if you put a little bit of extra mass around the equator, then this whole project made a whole lot more sense. Then you would actually match the data. But there is no way to put some extra mass around the equator. Nevertheless, there is some process, most likely, that mimics the effect of extra mass. So this gave us a clue. So we scratched our heads, and basically what actually worked in the end, after like an exciting summer, were models where you give up the idea that the whole planet rotates uniformly. So they're gas planets in principle. Every layer could orbit or rotate at a different speed. And it works quite well if you made the equatorial region rotate faster. It's called super rotation. You needed about 3 to 4% to rotate it faster than the deep interior. If you spin up the whole planet, that does not work. But it works if you make the equatorial part run faster. Then you have an extra centrifugal force. You actually, this is the standard oblateness from uniform rotation. If you make the equator rotate a little faster, you get this extra oblateness. And that actually helped us match the gravity field. So that was the key idea. And then someone said, you know, with this super rotation near the equator, people measured these things. And so then we looked at what cloud tracking observations had been done. So they looked at the clouds, but nobody before we had these measurements thought that they would lead just to this gigantic gravity signal, because there are clouds. If you look up at the sky, the mass in clouds, it's ludicrously small. It doesn't affect the Earth gravity field. But here in Saturn, it does. If you assume that the clouds that were tracked represent deep cylinders that go inside the planet. So then we basically constructed models for Saturn's interior where the clouds on top would go into the planet and would be approximately 9,000 kilometers deep. So that was the game-changing idea. We basically took the observed cloud motion, so rather saying they're just in a thin layer of the clouds, they go deep inside. That changed everything. That allowed us to match the gravity field, and then all the models all of a sudden make sense. And we had like the models put together. We have between 15 and 18 Earth masses where colleagues say this is plausible. And there's also there's some heavy elements in the hydrogen and helium envelope. And they're still arguing whether the amount is right. But overall, with the assumption that the planet doesn't no longer rotate uniformly, but you have these really deep winds, all the things started to make sense.
So when you say not uniformly, is it,
yes.
You're talking about depth right now or latitude?
That is all latitude, yes. So we do not have any longitudinal dependence in these models. So you see if there's storm systems on Saturn, but they are not massive enough to change the gravity field. So therefore, we have no longitudinal dependence, but latitudinal dependence we do. And we say the whole equatorial region just is about 4% faster than the deep interior.
Okay, so this is maybe an intuition that kind of is very weird for people who think about Earth, right? So what you're saying here is, well, first of all, you're saying that the clouds are moving fast, and that really means that the depth is moving fast.
Yes.
Right? The other one that I think I just got is that different parts of Saturn are moving at different speeds, right? That the equator is really like shearing itself relative to the higher latitude. So you really should be thinking of depth of Saturn as if it's the Earth's atmosphere.
Exactly. So it's a fluid planet. You can have shear from where one cylinder rotates at a different rate than another.
All right. So then, go on.
Yeah, go ahead.
Oh, so then you would get phenomena like vortices, like we have wind going from south to north and moving at this, like curve because of different rotations of different parts of the Earth. Presumably, we have that stuff internally to Saturn now.
Yes. So on Earth, it can't happen because the crust is rigid. But on Saturn, on Jupiter and Saturn, actually, there is no reason why it couldn't. So the cloud motion that you see, we extrapolate them to the deep interior, and it's done on cylinders.
Okay, and you're going to have the same kind of hurricane, like structural hurricanes inside of Saturn.
Yeah, except a hurricane is something local, while we assume it's a whole cylinder that rotates at a specific rate.
Okay, got it.
Okay, so that's the one part about Saturn itself. The result was that the winds that you see are extremely deep. The other side was equally interesting, and that relates to this mass of Saturn's rings. So the rings have an exquisite structure. Most of the mass is in the B and the C and a little bit in the A ring. They're opaque. And basically, there are gazillions of particles all going around the planet at Keplerian speeds. And there are some perturbations inside the rings, but basically, they're extremely thin. If they wouldn't be thin, particles would collide with each other. So what was not known, at least from gravity, how much material there was in the planet, in the rings. So what our colleagues basically figured out that the mass, all rings combined with gravity measured for the first time, they basically make about 30% of a Mimas mass. It doesn't tell me anything. I'm sure they will not tell you anything either. A Mimas mass, if you have 2,000 of those, a lunar mass, you need 16,000 to make an Earth mass. So why does it even matter if it's 0.4 Mimas masses? The reason is you can translate this into an age for the rings. And that you have to let sink in. So based on this mass measurements, we're saying that the rings are between 10 and 100 million years old only. I thought when the planet was formed, the rings were formed with it. And this result, this mass measurements completely contradicts the idea that the rings are primordial. So something relatively recently made these rings. So at around that time, there were still dinosaurs roaming on our planet. So the rings are extremely young. And let me just now sort of explain how that argument is being put together, how you relate mass to an age. And it's basically, you know that the rings become progressively darker with time because the micrometeorites that swirl around the solar system that hit the rings. So you approximately know what's the influx of dark material that hits the rings every year or every billion of years. That's being not very precisely known, but this is reasonably well characterized. So now imagine you have a sandwich, you have some butter on it, and you sort of have a pepper shaker, and you keep constantly adding pepper, and you stop when you have a specific color that you want. That's the same argument. We know how the rings, how dark they are today. If you assume they were pristine ice, perfectly white initially, and you know how much dark material you're adding, and now we know how much mass there is in the rings, we know how long it took till they reached today's color, and therefore it's important. So if they're so young, we're actually lucky enough to see these rings because they may not be there forever. They may gradually degrade and fall into Saturn, but also it points to a fact that there was a process that generated them. What gave rise to these huge number of particles? And there are different ways. Either you have a giant collision, or you basically some type of object hit another moon at that moment, and then you have a gigantic collision. Millions of particles, billions are created, and then the rings form from the leftover material. If you're outside the orbit of the rings, and you go around the planet, you're going to guarantee to hit the planet at the other ring part at some point. So the rings are a stable configuration. But nevertheless, one idea is you have a Kuiper-Belt object that hit an existing moon. Another interesting idea is you maybe had 3 moons, and they can maybe shift a little bit in their orbit and then get in a resonance. And when they're in a resonance, they perturb each other so that they actually can lead to another giant collision. So the message here is the rings of Saturn are extremely young. So the next time you have a binocular, so you have some telescope, look at them, admire them a little bit more than you would otherwise, because they are not, they may be gone in another 100 million years. So this went over the internet, people really liked it, but the best comment came from a Russian website. And that person had the idea basically saying that the headline basically said in Russian here, the astronomers had learned when Saturn became the Lord of the Rings. So that was a nice touch. So are there any questions about Saturn? Otherwise, I'm going to switch over to Jupiter.
One more thing. So the argument was, we know the current mass, we know the inflow of dark material, so we can work backwards. How do you know the inflow of dark material?
So that is not my expertise, and I trust my colleagues. We characterize it approximately by crater counting. So all craters on all objects like the moon and other things have been very, very carefully counted, and that you can estimate how the influx of lidaritic material really died down over time. And then you have some estimates how often Jupiter gets hit with these things, like there was Shoemaker-Levy and other things. So there are measurements. I'm not exactly sure what they're based on, but it's clear that you have an error of 10. So these are order of magnitude determinations.
Right. Okay, thanks.
Okay, so let's switch on.
This collision.
Yes.
Sorry, just one more follow-up. Did this collision have to happen in the neighborhood of Saturn, or could it have been further out?
You think so, because otherwise Saturn wouldn't have captured all these planetesimals. It's hard to make such a large, it has to be, you have to be confined to the gravity field of Saturn. So in the process, people do simulations for the moon forming impact around our planet, and the Earth gets hit by a Mars-sized object, and it has this disk of debris material forming, and out of that disk you have a the moon forming. So in this case, we're saying a similar process happened, except there isn't enough mass for the rings to form a new moon. So it may seem bizarre if you're not in this field, but if other people talk about these processes, it's quite normal at this point. Okay, Juno mission. Juno mission actually still goes on. The spacecraft flies by every 2 months and makes new measurements of the gravity field and of the magnetic field and other things. It was launched from Cape Canaveral. I do models for the interior. The launch was in 2011. And there was an Earth flyby to give it an extra gravity assist to make it reach Jupiter faster, and arrived in 2016. So it's a spacecraft that has huge solar panels because it's not nuclear powered. So it's one of those things, maybe in the future, we don't have to launch them with nuclear power if we are good enough and efficient to do so with big solar panels. Here's a big box that protects the equipment from the charged particles that are trapped in Jupiter's magnetic field. So every time the spacecraft flies by, it goes through that region where lots of charged particles are and there's torus around it, and they can potentially do damage. So we're all keeping our fingers crossed, nothing will happen, but it could happen that whatever, like your old hard drive sometime dies, sometimes it hits something crucial. Nothing of that has happened, but we are aware that this mission will not last forever. So we all went to JPL to follow the orbit insertion when it arrives after 4 years of flight. The thrusters are fired, it slows down, and it goes in these 2 long orbits of 54 days. And then there was a second maneuver that puts us in 14-day orbits. So we're all there. We all sort of watched the event with a 45-minute delay because it takes a little while for signals to arrive. And everything looked perfect. We're all happy. Everything was essential. Nevertheless, in between the first braking maneuver, and we're supposed to go in this faster orbit, the data was reanalyzed, and it was actually so determined that the valve that mixes the hydrogens and the oxygen carefully did not open properly, and there was a mixing problem. So the risk was that if we ever fire this main thrust engine again, it could be a gigantic explosion, and there would be a loss of mission. So it was determined that we should not do this. So we stayed on these long 54-day orbits as a result, and now the mission is a bit longer. So it's rocket science, so be careful. Nevertheless, it took spectacular pictures of the cloud motions to higher resolution than we had before. And this is not my specific expertise, I have to admit. But it's basically ammonia clouds are typically white, and when they're not there, you can look a little bit deeper, and you have ammonia hydrosulfide, which has a brownish color. The exact composition is actually not quite understood at that moment. So in the polar region, I think that's the South Pole, you have these cyclones. They're pretty stable over a number of years, but not infinitely. Sometimes one moves out and one moves in. They're relatively shallow based on what we know. So my job on that mission was to interpret the gravity field. And that was equally challenging as understanding Saturn's field. In typical models like shown here on the left, you can match J2, but we had extreme difficulty matching J4 and J6. And we can match them with unphysical assumptions, but if you want to make good physics and about hydrogen and helium, how we think they behave, then you're here. So, and then the data is here. So what is predicted, you have wind motions like that helped us to solve the Saturn problem. They're only predicted to make this signal. They're not massive enough actually to put us over here. So there was this gigantic discrepancy that puzzled us for several years. How do we make physically motivated models that make sense from the interior physics and still match the spacecraft model? So there was a little bit of a clue, and that's the concept of a dilute core. So if you're not saying that these heavy elements are concentrated in the center, but they're a little bit smeared out, then at least it moves you a little bit closer to the actual data. So that was done in 2017. And we've just basically changed that idea, made more models by making it more extreme. And what I'm basically saying here with the dilute core is that we're spreading out the material to 50% of the radius. And inside that region, we have heavy elements, but they are diluted by hydrogen. So there's hydrogen and helium made up about 83%, and 15% are heavier elements. And then this big object with 50% of the radius, then the heavy elements, they die down to something quite modest, to something that's compatible with the solar composition. But basically then we're over here. So by taking a concentrated core and diluting it over 0.5% of the radius, we basically make it happen and then match the Juno data with J4 and J6. And we need a little bit of a wind effect. So we've put together these combined models where we have some interior parameters and we have some wind parameters, and we put it together in some models. We have some giant optimizer that adjusts both of them. That allows us to put together a model that matches this perfectly. We have a dilute core combined with this wind. So, and yes, so the region here is like 16% of heavy elements, realizing the rest of it is hydrogen and helium. So that's what people have never done before. So if you put it all together, then you have a region where you have a dilute core. It's mixed most of the magnetic field. Then it has a region where that composition is changing. That typically means the planet is not convecting. And you have another region of metallic hydrogen where you have another region to make a magnetic field. And you have a region of helium rain, and here you have a molecular region. So that is now a new, like, 5-layer model, if you like. And the colleagues who study and model magnetic fields, they're quite happy with us because we have two magnetically active region. You can make a complex magnetic field. So this is what they've measured. It was not a simple magnetic field, it was a complex magnetic field. So this is what we're proposing right now. Some of my colleagues have raised some eyebrows because typical models are used to having a compact core. It was saying if you have a compact core, you cannot match the gravity field unless you make some unphysical assumptions. So this is basically how the models looked before. How they look now is we have really deep winds in Saturn. And here we completely changed how we understand Jupiter's core. We think it's dilute, and it's no longer then, it's just a lot of hydrogen and helium in that core region. Then it all makes sense. All right, so basically the message here is Jupiter has a significant diluted core. So this is very large. You can see it by this red region. All right, this is all I wanted to say. Thank you very much. If you have more questions, I'm happy to answer.
Well, let me ask you this. I didn't go ahead and send a message about the core specifically for magnetism. It sounds like you're saying there's 3 separate dynamos and 3 separate layers that are driving a single magnetic field.
Yes, so even before we came up with this, what had happened is the people published the magnetic field data. And they said, if you have one dynamo region, then you should get a really strong dipolar region without these variations here. So there's a strong dipole field, but there shouldn't be these isolated. There shouldn't be this blue spot here. Because if you have a simple dynamo, it make a gigantic dipolar field, and that's it. So they were already looking for a way out to actually look for the structure in the magnetic field. So we helped them. We have 2 dynamo active regions. So we have the core, which is dominated by metallic hydrogen, and then we have another region, again, metallic hydrogen. And out here, hydrogen is molecular. So in this region, the conductivity is low. So you cannot make, you cannot make substantial contribution to the magnetic field. It's just not conductive.
Okay.
Are there implications for layers that are accessible for humans in any sort of reasonable way? Like I kind of got the flavor of this with Saturn, in that like if you could actually land, you'd have to go a lot deeper than maybe we thought before. But like this is a wild idea, but just in terms of like mining, could you have a probe around a planet, find that something is new about a layer that might actually be accessible if you landed on that planet, for that purpose of mining?
Yes, so that brings me another question. My son at some point said, well, Dad, all your work will be eventually done by a computer. And I was wondering, that related when I got your invitation, why would you do this in 10 years? And the answer is, if there are lots of spacecraft being launched, the same way we have the number of satellites around Earth, if you actually have many, many spacecraft visiting planets, it becomes so cheap that lots of people will do this for one reason or the other, then you as a company will actually do these analyses. So now the question, what could be done in the future? It's probably unlikely to land because there is no solid surface. And we dropped the probe in the interior of Jupiter, and that went into pressure of 22 bars, and it became so hot that it actually stopped functioning. So we made some measurements beforehand. So landing is unlikely. But nevertheless, what people want to do is something like seismology. So seismology is the field that studies earthquakes, but also there's something like normal modes. So an object swings according to its natural frequency. So once you have your guitar string and you tuned it, it has a very characteristic frequency. Planets are the same way. The Earth is the same way. So what people try to do, to really carefully track the cloud motion, and then determine these normal mode frequencies. Once you can do this, then we have a much better understanding of the interior. So then we'll see whether this is all right or it's all ludicrous, and people will come up with a different explanation. But that's the best shot we have. It's not to land, but to observe the surface so carefully. You can do a Fourier transform of different parcels on the planet, Fourier transform this, and back out what are the frequencies of the normal modes of a giant planet.
And then in the future, it's going to be like dropping probes, seeing where the wind, like Saturn, you said, like the winds are really deep. So those structures, if you can track them, you should be able to get at the real depth of Saturn, because, right?
Yes, true. But basically 9,000 kilometers, that is basically, I don't know, not another megabar, but it's basically, it's like several 10,000s of bars.
So we've never,
it will die. And then ironically, I didn't know this. I thought it's like, it gets crushed like a submarine. No, that did not happen. It was crushed like from heating up too much. That is the main problem.
Interesting. So then, is your simulation hydrostatic? I mean, do you actually model winds directly?
We do a hybrid approach. We have a colleague in Israel who's doing these winds very carefully, non-hydrostatically, the same way you just alluded to. When we do the winds for Saturn, we actually do the winds hydrostatically. And that is a way, as long as the winds are on cylinders, you can actually do them hydrostatically. So that's the hybrid approach for Saturn. For the Jupiter work, we actually adopted the probe from our Israeli colleagues and actually do them non-hydrostatically.
So when you say they're in a cylinder, it means you have a 1D approximation for the winds?
Yeah.
Like one of those planetary cone things?
Planetary cone, I'm not sure.
I'm trying to relate your simulation to what people do for climate models or weather models for the Earth, where they try to do a fairly high granularity.
Yes, so basically, not cones in that particular. So in the models for climate simulations, they're essentially 3D, and you have a very fine resolution in latitude, longitude, and then vertically. You have a coarser resolution. We don't even do this. So we have no dependence on latitude. So that puts us on a 2D model, yes. And
Okay.
then we even our depth dependence is extremely simple.
Okay, so
Yes.
we should be thinking like a circle with a lot of depth. That's your model, without worrying about like like the north-south direction.
Let's go back to the slide.
Yeah.
So
I guess I'm trying to figure out what your modeling assumptions are, what the constraints are, kind of what's driving these decisions, and what's good enough.
This decision drives that we need. We want to understand the gravity signal, and that requires a lot of mass. So if you have a complicated cloud model with lots of 3D structures, you cannot argue that there is a lot of mass involved. So there's no necessity to make this more complicated than we do already. But what is necessary? That we have a lot of mass involved. So basically what this picture here is, we say the clouds retract at this particular location. And then it's the same everywhere. So latitude in
Got
the
it.
planet. And then that parcel of fluid has a certain angular velocity. And that, if you go deep down into the planet, so here basically you're down here, but we're saying this rotates at the same speed as the fluid up here. So that means by cylinder, the whole cylinder rotates at the same velocity. That's what we assume, and that matches the gravity field. And the most the signal comes from the outer part. So in the interior, we cannot match, our Israeli colleagues can match these observations also, but then they assume that the winds penetrate to several thousand kilometers and then they stop.
Got it. So then maybe this is a good slide for this. So what I was asking about for wind, relating Earth winds and Saturn, deep winds, is you have the Coriolis like winds, right? You say like, if you have any motion, which I'm not sure happens in Saturn, if you have motion of air from equator to the North Pole, you have North Pole spins much faster, effectively, because it's smaller, right? So what you have is this funny shape. The winds don't go like this; they go like in a weird curve, like around. I'm not sure where. So with the spin or without the spin, I can't remember this, but I'm not sure if these funny shapes where these are turning winds as opposed to just straight winds. I mean, what does this go? Nothing, just it turns like as.
You mean Hadley cells, or what you're referring to?
Oh, trying to remember this. See, I'm not a climate person. So yeah, I guess I'm trying to figure out these. Because it's a much more fluid planet, I'm trying to figure out if there's like large structural shifts going on all the time. I guess sort of like the Earth's mantle. It's all boiling all the time.
So yes, so you have convection that cools the Earth mantle, it drives plate tectonics, and that's how the planet cools. So that also operates on giant planets. So, and that's sort of built into the models that we construct. So you also have, you're right, that the planet receives most of the solar radiation near the equator and very little near the poles. So you have to have a way to transport heat from the equatorial region to the poles. And that gives rise to the Hadley cells on Earth and also gives rise to the jets on Jupiter. Okay. So this is all true. But nevertheless, if you want to explain the gravity field, that gives rise to something that we didn't appreciate before, that these winds need to be very deep. While if you want to transfer the heat from the equator to the pole, you can do this quite with shallow parcels.
Got it. So that's the new constraint. So the previous constraints were speed of winds. Do you have temperature?
Temperature is constrained by measurements in the outer part, and then
you had those
extra. Yeah.
And the future measurements are going to be the seismic ones, which is going to be another century before we can get those.
Well, not really. Ironically, the Cassini spacecraft, they measured something for Saturn by using the rings. So there's a paper coming out, so that there are few of those measurements. And one of the colleagues on the mission, they're trying to do this for Jupiter. And the debate is whether they measured something real or they just measured noise. So it could happen tomorrow, it could happen in a decade.
They're doing seismic stuff from outside. So wait, what's hitting the planet then? Or am I misunderstanding this?
The planet is like your guitar string. The planet by itself will have these normal modes excited.
Okay.
So you don't need anything to hit them. It's not an earthquake. It's basically
Yeah.
normal modes. They are excited to some degree already. So the question is, how do you probe them? And in this case, the irony is that the wings of Saturn are a good probe for a limited number of modes of Saturn. So that has been shown in the last years. And I have a colleague, Chris Mankiewicz, who is the expert on this, and you should invite him to give another talk if you're interested.
Interesting. Cool. Yes, Paul. This is fascinating. Garrett, did you have anything else? Because we're almost at time.
I just wanted to know if there's like a probabilistic or uncertainty element in the modeling.
So depends a little bit. We all use Monte Carlo simulations to map out the allowed parameter space. So that's embedded in all the simulations that we do. But often the ensembles we construct, none of them matched the actual data. So we use Monte Carlo methods to make that happen. But often they're just a tool. The assumptions are more important.
It makes sense. So actually, maybe like ask this: is it possible to, in social simulation, assumptions are kind of garbage for very good reasons. Psychology is incredibly difficult. So there is a desire to be able to learn the structure of like what's a good enough explanation of human society and so on. And there's not that much progress in that because it's pretty complicated. Here, is there a notion of generative creation of like a machine says, I wonder if I put more mass here, what can I reproduce results? Like, because you can evaluate thousands of such hypotheses in the computer.
Yes, so we have two missions, right? For 2 planets and 2 missions recently. We're also starved for data. It could be different in the future. So therefore, with the limited data set we have, we also, everything we say about these planets has other assumptions built in. For example, one of the elephants in the room is how dense is hydrogen in helium. So it turns out if you say, you know, we had good evidence why we think hydrogen has that density at 1 million atmosphere. But if you tell me it's 10% different, then the model predictions about the dilute core would change. So that's built in. We're looking for the most plausible models. You have 15 models, you pick the one that makes the most physical sense. And I think your conclusions about the interior will depend on which model you choose, yes.
And a lot of it would be like you have multiple sources of like you have all these high density experiments. So any one of those guesses has to be consistent with those experiments too. They're part of your simulation effectively. And there are error bars.
True, but they all have error bars, they all have assumptions. And it could happen tomorrow that someone does the measurement 10 times better than in the past, and now all the models have to be updated. That cannot be ruled out.
Yeah, that makes sense. All right, well, thank you. This was fascinating.
All right, thank you so much for the invitation.